miss a few of those cardboard cutouts and get my wife's face put on it. Now, it could go both ways, right? Well, give us a friend with things that you choose now. Exactly, and sometimes, your wife's going to be picky at times with pictures, and I hope I choose the right one, but I think, in the end, she'll probably be quite excited and touched by the whole thing, if it's possible. I'm sure it is such a great idea. Wayne McNeil talking to me at the end there. We were also hearing from his fellow Facebook commentator, Richard Wang. That is it for this edition of Newshour. Thanks so much for being with us. I'll be back at the same time tomorrow. Until then, stay safe. Bye-bye. Support for GPR comes from Rome's Pizza, serving San Antonio since 1990 with curbside pickup at 3 locations: Days of Olive and Darren and Tranquil Roads. Online ordering for delivery or carryout is at romespizza.com. Support for GPR comes from Wild Birds Unlimited Nature Shop, now offering gift ideas and gift cards for Mother's Day. Curbside service available. Call-in orders for Wild Birds customized service and pickup instructions are being taken at 479 Bird. News and Views, KSTX, San Antonio, on the air at 89.1 FM and online at apr.org. It's 10 o'clock. COVID-19 seems to be receding in larger Texas cities. A rise in cases in smaller ones as those front lines getting hit especially hard. The latest today on the Texas Standard.
All righty. Got one more people. Let's wait a few more minutes. Let me put the slides up. I'm going to start with the angiotensin lab handout that I sent you, or it's actually basically just the lab handout that I sent you. We'll go over that. And then we'll finish up the problems from Monday. We'll see how much time we have left. That's fine. I was accepting them late. Did it work well loading it up? Ha! Okay, well, we'll learn. We will learn. Yeah, I saw a bunch of you put the Cambridge worksheet in. That's fine. I'll look at them tomorrow probably. Okay, let's go ahead and get started real quick. Yeah, I can make a separate folder. You mean for the homework stuff, or is that what you're talking about, Nicholas? Okay, yeah, okay, I'll put them in a separate folder under homework for Mass Spec. I need my own folder. All right, we're going to do a couple of experiments virtually, I guess, since you guys aren't allowed in the labs, which may not be necessarily a bad thing, but that's the way things are. One of the things we do for Mass Spec is protein peptide sequencing. In other words, figuring out what the amino acid sequence is of a protein or a peptide. So for the quadruple ion trap liquid chromatography experiment, we use what's called angiotensin 1. It has the following sequence, and it has the following mass depending on what free base you have it hooked to. So generally we look at the mass of 1296. Remember, if we're doing mass spec, we're not going to worry about average molecular mass. We're going to look at monoisotopic mass, because that's what the mass spec is going to give us. So we've talked about some of this already. It's sort of a busy slide, but depending on how many carbons you have is going to determine whether this first peak in your sequence of peaks for your compound, for your protein or your peptide, is going to be the 100% peak. We start out with 70 carbons, we go to 108 carbons, we go to 183 carbons, and then we go to 275 carbons. And I know these are sort of in the way. So what we're trying to point out is that when we have 70 carbons, the highest probability of having all carbon 12s is your A peak. You got at least having a probability of having 1 and 2 carbon 12s. I got to work on the slide. If you go to 108 carbons, at this point you're close to having the first two peaks be 1 to 1. The all carbon 12 peak is going to be roughly equal intensity to the protein or peptide containing 1 carbon 13. Once I get past that to like 183, you're going to see this all carbon 12 peak is going to be smaller than the one with carbon 13. This means that you have a 100% chance of having a 1 carbon 13 in that size of protein or peptide. In other words, something that has 183 carbons. And if you go to 275 carbons, and again, these are smallish peptides, proteins. I mean, it's, if you're doing biological mass spec, it ain't hard getting to 275 carbons. But at this point, the first peak nor the second peak is your most intense. Your third peak, your one with 2 carbon 13s, is 100%. So you got a 100% chance of having 2 carbon 13s. So why is this important? Well, if you look at the envelope for your compound, for your protein or peptide, depending on where I got to draw my little, damn it, I forgot the pointer. It worked well on my screen. Somebody needs to scream at me. So if you look at the envelope of these guys, depending where the maximum of the envelope is, can give you some idea of how many carbons are in your molecule. So you not only have the mass, but you can tell, is it really carbon rich or is it something else? That can and cannot be handy. What else I want to talk about here? Yeah, okay. Next. So a couple of ways. When you're doing protein or peptide sequencing, if you're doing mass spectrometry and you're doing collision-induced dissociation, you're generally going to get Y-type ions and B-type ions. So do you all remember have you all had biochemistry or not? Yes, no, maybe, maybe not. Wasn't a fan. Well, I wasn't a fan either, but it's still good to have. Okay. So the B-type ions maintain the amino acid end, and you're basically flushing things off from the carboxylic acid end. The Y ions are basically maintaining the carboxylic acid end of it, and you're pulling things off the amino acid end. So it basically means from which end of the protein you're slicing off the individual amino acids. So the common one that you're going to be able to put protons are any of these amine-containing amino acids. These are like to grab protons. So things like histidine is really good, and phenylalanine is pretty good. Notice we're going to put the mass to about 2 decimal places if we can. If we're doing sequencing, we're going to need something like that. Here you have a table of, this is from, you guys can go to it. There's lots of tables out there. If you need one, I can post one on the Blackboard. You got the structure of the amino acid, you have the monoisotopic mass, and you have the average mass. So for all the stuff that we're doing, we're going to be using the monoisotopic mass. All right. Now, what else do I need to talk about on this one? Yeah, what do you notice about these amino acids? Anything? Yeah, no OH. I said it looks like no O. No, it's no OH. You got missing the hydroxide here and missing the hydrogen on the amine end. So from a mass spec perspective, when you're calculating the mass of your protein or peptide, you don't worry. You want it without the hydrogen here and without the oxygen here, because that's what you're basically breaking out of water when you string these things along. So the monoisotopic mass is without these having the OH on the carboxylic end and the hydrogen on the amine end. This means that when you're putting all this together, once you've used these numbers to add up all the masses, depending on what your sequence is, you got to add a water to it. So you got to add 18 to the mass that you get in order to get the mass that you're going to have in the mass spectrometer. So our typical LCMS, if you were downstairs running this properly, you would see something like this for angiotensin. These are actually a lot of peaks for one. Oh, well, hold on. Let me go back. Now I know what I wanted to ask you guys. I won't ask the question. Let me just make the point. A lot of people, when they see multiple peaks here, are going to go, well, I got 3 different compounds here, or 4 different. No, this is one protein. This is one single protein. All you're seeing is the stable isotope abundance distribution within that set of molecules. So the next question is, when I'm looking at mass spec, how many molecules am I generally looking at? If I was looking at one molecule, I wouldn't see all these peaks. I'd see one of these. I'd just see one of these peaks. In mass spec, if we're talking nanomolar concentrations, you're talking about what? 10 to the 23rd minus 9, which is about 10 to the 14th. So maybe 10 to the 14th, 10 to the 13th molecules. Within that many molecules, you're going to have a natural distribution abundance of the stable isotopes. All right. So even though you got 5, 6, 7 peaks here, this all belongs to one protein. All right. They're not 4 different compounds or 6 different compounds or yada yada. So that's sort of different when you're dealing with mass spectrometry. All right. So this is angiotensin. This is probably in the 2.5 picomolar range. If I remember right, this was taken a while back. This has also been acidified, so it's probably a pH of maybe 4.5 to 5-ish. I would say it's closer to 4.5, more acidic than usual, simply because of this peak that we see out here. So again, this is one species, angiotensin. I'm getting a whole host of different peaks for it. So your molecular ion is your protonated molecular ion is at 1296.6 out here. Since we've talked a little bit about proteins and peptide previously, the 649.9 is your doubly charged ion, and your 433.9 is your triply charged ion. And this is why I'm saying the pH is probably lower than 5, is the distribution of the triply charged versus doubly charged versus singly charged is very, very pH dependent. So the lower the pH, the more protons you have available, the more likely you are you're going to have a multiple charging. In this case, the base peak is the triply charged ion. Recall what the X and Y axes are. The Y axis down here is relative abundance, relative to everything else you have. The X axis is mass over charge. All right. And then up here, we basically look at different things that the mass spec is doing. This basically gives you a intensity value. This tells you this is a full mass spec in positive ion mode. We're scanning from 325 to 2000 M over Z or Daltons. A couple other things you're looking at are these peaks here at 1318.6 and 1362.6. This is about 22 more than your molecular ion. This is due to a sodium adduct. And this one is due to a potassium adduct. So we had a kind of a little salty situation. Notice how this is the same thing. You're going to have the doubly charged ion, the doubly charged with 2 sodiums, with 1 sodium or 1 proton is that probably. So this is a difference of 11. But notice how much closer they've gotten. So this is basically a difference of 22 mass units. This is also a difference of 22 mass units, except since it's doubly charged on our mass scale, it's going to appear as a difference of just 11 mass units. All right. Any questions on that, or do you want to think about it for a little while? So what we're going to do for the, and not right away, but the idea of the angiotensin experiment is going to calculate the M to Z for charges +1, +2, or +3. And you want to calculate all possible Y fragments with or without water. And again, remember the leucine is the carboxylic end, the asparagine is the amino acid end. So you're going to put together a table that looks like this. You're going to have all the possible Y fragments, so this is the whole thing. I've cleaved off an asparagine here, and an arginine here, a valine here, tyrosine. We slowly cleave them off. We get these masses. I then go ahead and add a water to it. And again, this is the unprotonated masses. So what you'd expect to see in your mass spec would be a one with one more, with 1 mass unit higher. So the idea then is to go into your mass spectrum and you start figuring out what you see. So you can do CID. So this is doing collision-induced dissociation on that 1296.6, i.e. the 1297 mass. So the 1297 would be here somewhere, and we get these fragments, and then you'd go, and these are all also, everything down here is probably reasonable fragments from the collision dissociation. So what you do is you take a look and see which ones, one more, which ones appear in the table. You're not going to see all of them. You're going to see the thermodynamically most stable ones. So that's a quick, brief review of the angiotensin experiment. We're going to get to that next week in terms of what we want to do for the online labs. What I sent out to you guys on Monday was the GBN experiment, so the base neutrals experiment. You have the data pack for that and the chromatogram. The goal is, what we're basically looking at is the EPA methods for organic analysis of municipal and industrial wastewater. It's called method 625. It's a base neutrals method. What I have at the end of that packet is a table. When you get done, all you're going to hand in is a table. All you hand in is a table. And what you need to be able to do is get the molecular weight, monoisotopic molecular weight. You want to go to the NIST web book and pick up the first, second, and third most intense lines. And also, just for fun and humoring me, throw in the chem abstracts number so I know you can do that. All right, so when the lab will be due on Monday. I will set up something in Blackboard. I think I can do that. We'll see. Guess I did it for the Cambridge, so I can do it for this. I'll set up a thing on Blackboard where you can just turn into Blackboard. It's mainly for my edification, so I can play with it since I'm doing an online class this summer. You can learn how to do all this online shit. And all you hand in is the data sheet. The data sheet is going to have all 18 or 19 compounds on it. It's basically just our first few compounds. So the goal is going to be, by looking at the first, second, and third most intense peaks in your fragmentation spectrum off of the GCMS, you can assign a retention time to each of these compounds in your base neutral mix. Again, this is just a standard mix you can buy, and it's used for calibrating and doing QA, QC stuff. If you're in an environmental lab if you're working for SAW, for example, you would be doing this pretty much every day of your life. because you're looking at municipal wastewater and you're trying to see this set of compounds. These are the ones that a set of ones on this method that are reportable to the EPA. And if you look in your saws, actually I should get it. If you look in your little saws once a year, we'll give you a list of things that they have. So next, from your packet, you'll all have this. You'll also have this in here. This is what your GCMS looks like. Your gas chromatogram, and this is just your GC. This is essentially your gas chromatogram. Notice we're running from 0 to 35 and almost 36 minutes. Down here is in minutes. These are in hundredths of minutes. So if you were going to report this peak, the retention time would be about 16.27. Or you can give a short range of retention times because they're not quite as narrow as you look. Remember, we're looking at 35 minutes here. Remember, well, let me ask this question in a really stupid way. So where's your mass spec in this? This is the gas chromatogram. So what happened to the mass spectra? I knew I needed more caffeine this morning. You guys, you can use your microphones. There's only 10 of you here. I don't know what you mean by add them all up. That doesn't make any sense, Nicholas. The peaks, yes. Remember, a GCMS experiment is what we call a three-dimensional experiment. The first two dimensions are your retention time, not your relative intensity, your relative intensity and your retention time. Each data point, and there's lots of data points to describe the peak, each data point in your gas chromatogram is a mass spectrum. So literally your mass spectrum basically are all the data points that define each of these peaks all along here. All right, so that's what makes this a three-dimensional experiment. So if I go ahead and click on one of these, I think I click on this first one. If I click on one of the data points in this peak, am I right? Let's see, yeah, 826, 820, yeah. So if I click on a data point there, it'll give me a mass spectrum. Generally what I'll do is I'll average several mass spectrum across the chromatographic peak. So here's your mass spectrum that you get. We talked a little bit about what different things look like. Can anybody tell me what halogen this compound contains? I told you what my favorite halogen was. Look at the 146, the 148, and the 150 roughly. So what you're looking at is the cascade of these peaks. And again, this is one compound. It just has a stable isotope that gives you this roughly, what is it, 150, about 20? Yeah, about that. All right, I'll give up. It's chlorine. So this contains one chlorine, whatever it happens to be. So I know, what is 147? 147 contains one chlorine 35 and one chlorine 37. This contains all chlorine 35s, and this contains all chlorine 37s. And just for fun, I'll tell you it's hooked to a benzene ring. If you look here, which is really cool, you go to 146, you go to 111 here. The difference between 146 and 111 is what? Either have your caffeine or have your whiskey. What's the difference of 146? Yeah, it's a chlorine. Very good, thank you. It's a chlorine. And notice how the isotope pattern changes. Here you got an isotope pattern of all of this. Make you feel dizzy, right? Doesn't follow. Here you got an isotope pattern for two chlorines. Got 111 and 113. You go to an isotope for one chlorine. No, it's not that it's bound. It's just that you basically are fragmenting it because of the 70 eV electrons, and you're getting different fragments. you go to here to 75, again, that's a difference of what, about 35 or 36? That's about 36. But that, again, is a difference of 1 chlorine. And here you've gotten the benzene ring. So it's basically a benzene ring with at least 2 chlorines and maybe something else if these are important. So I'm not going to sit here and expect you to go through this and work out all the mass spectra. How do you think I expect you to figure out what's what? Compare to standards. Very good, Nicole. And where are you going to get the standards from? Yes, the NIST data, the NIST webbook. So the reason I gave you, let me see. Let me go back. So the reason I gave you the names, and I'm asking you to find the CAS numbers, is so that you can go to the NIST webbook, look up the standard mass spectra for these, and they're doing 70 eV electron impact fragmentation spectra. You go to the NIST webbook and you put in number 1, number 2, and number 3, and then you compare it with the handouts that I've given you as to what compound it is. So in the handout, I'll have printed out a mass spectrum for each of these peaks. So let's go back and figure out what peaks we're going to pick out as our 3 peaks. My eyes are itching. Allergies. So in this case, you may want to say, well, my biggest 3 peaks are 146, 148, and 111 or 75. And I'd say, yeah, you're kind of right. But the thing is, there's no point in putting down the 148 as your number 2 peak. Why is that? You're right, it's the isotope. This is not a unique fragment. It's basically an isotope related back to 146. So what you want to do is for your number 1, number 2, and number 3 is put down 3 unique peaks. So in this case, it would be 146, 111, and 75. Everybody kind of see that? Does that kind of make sense? Yes, no, a few of you are awake. All right, let's go to the next one. Good, okay. Again, we have another compound here. And notice I'm being very cagey. This has a lot of different isotope pattern peaks. Again, can anybody tell me what the halogen is here? Nope. Go one up. Chlorine. Very good. Thank you, Daniel. It's chlorine again. So if you were going to put in well, first of all, let me go through here. Again, we're looking at retention time. Here it says retention time from 11.32 to 11.38. So that would be 11.32 to 11. So that would be this peak right here in your chromatogram. 11.32 to 11.38. So I basically averaged a bunch of data points across this peak. All right, and in this case, I would be picking about 260, 225, and maybe this one here, either the 190 or the 188. So those would be my 3 most intense peaks. You all see that? Does that kind of make sense to everybody? Any questions on this? Okay, good, Nick. Why not 259? Well, it's 259.6, so I was rounding up to 260. Or, I mean, you may want to pick this. You're talking about, do you want to pick this one here? That's a good question. because this would be the lowest mass monoisotopic peak would be at 258. So yeah, I couldn't say, yeah, 258 wouldn't be wrong. You're right. I probably want to pick 258 here because that's the lowest abundance peak. That starts the whole cascade out. This is a peak with 1 chlorine 37, 2 chlorine 37s, 3 chlorine 37s, and maybe even a 4th chlorine 37. And if you notice, this goes from 258 to 223. Again, very nice. You lose your chlorine. You go from 223 to 188. You lost another chlorine. And what I find so fascinating about this is how the isotope pattern changes as you lose 1 chlorine from here to here and the 2nd chlorine from here to here. So you can literally see that chlorine, the stable isotope pattern changing and adjusting depending on how many of the chlorines you have on there. All right, so this is why I love chlorine. It's just really indicative. It has a really unique stable isotope pattern that doesn't hold any water against the cool stuff you can see with some of the transition metals. But for a main group element, it still has a cool isotope pattern. All right. Then you're going to come across something like this. You got the 152. And then you got the 126. There being so few fragments, I mean, yeah, you got some carbon-13, you're losing a few hydrogens here. There's a little bit of hydrogen loss here, but those aren't really all that important. You got essentially 2 peaks. So I'd report the 252 as number 1 and the 126 as number 2. What is this very clean electron impact, 70 electron volt electron impact fragmentation spectrum tell me about the compound I'm looking at? What does it have to have? Yep, lots of conjugation. Delocalization, conjugation. You're more than likely not pulling any electrons out of a bonding orbital. These are all delocalized electrons. This is something you would very typically see for your family of compounds, which all of you know as polyaromatic hydrocarbons. Your anthracenes, your phenanthrenes, and your, I guess chrysene is one or not. Yeah. Anyways, there's several polyaromatic hydrocarbons in this text mixture, and this is very typical. And in this case, 2 is good. I mean, yeah, you could kind of say say something about the 113. Yep, polyaromatic hydrocarbons. Now, so the other thing to realize is this peak at half of 252 is due. Why is this half? Did the ring just break apart in half? Did you put enough energy in to slice the ring in half? I was using my superconducting electron beam tweezers and cut the molecule in half. I know, I've been sarcastic. So what's the 126? Remember, your scale is m over z. You're dealing with something that's really, really conjugated. No, go the other direction. Reverse that vector, Daniel. You're dealing with m over z. M is 252. In the case of 252, z is 1. In the case of 126, it's z is 2. Does that make sense? So you got something that's the monocation and the dication. So this is probably a radical cation, and this is probably just a dication. And this is pretty typical for polyaromatic hydrocarbons or anything with a lot of conjugation in it. And that is, you will see a doubly charged. So whenever I see something this clean, I think it's polyaromatic. I'm going to go look for something half the size. And if I see it, I'm going, okay, it's some kind of a polyaromatic hydrocarbon. And I've already narrowed it down to at least a class of compounds if I'm not sure what's going on. So this is the peak, or this is the, my brain's gone. This is the mass spectrum from the NIST Chemistry webbook. There is the web link to the webbook, which you'll be needing. This is the spectrum for benzanthracene. And it looks like, and again, you see the very, very clean fragmentation spectrum. You've got something here, which I guess is about 223 if memory serves me right. And then this is going to be about 112, 111. So you got this half peak. All right, and again, you'd report 1 for this one, number 1, and that would be number 2. So you're going to go look at all the mass spectra in the NIST webbook, fill in that chart as to number 1, number 2, and number 3 most intense peaks the way we just discussed it. All right, and then you're going to go and look at what matches in the set of peaks I gave you, and then if you get something that matches it, you're going to report this retention time up here, so 28 in this case. All right. Finally, you got bis2 chloroethoxy. Yeah, it's due Monday. Monday, 5 p.m. Okay, I don't know, sometime on Monday. I'll make it. I'll basically load it up in the Blackboard as Monday at 11 p.m. If you want to do it that way, I'm fine with that. This is going to be one of them. You're going to have one more. We're going to do the angiotensin next week. I kind of just wanted to give you a flavor for the angiotensin. We're going to talk about some proteomic stuff on Monday, and then I'll let you guys just do the angiotensin lab that way. Does that sound okay? When's your quiz? Oh, I'm going to probably give you a take-home quiz end of next week, so probably Friday, maybe Wednesday, depends on what we cover. I think the best thing is a take-home quiz for this right now. It'll be a combination of things we've talked about in class. Or, I don't know, maybe we'll just do the labs and count the lab grade as a quiz grade. We'll see. I'm not wedded to giving you all a quiz under all these circumstances right now, to be honest with you. If you guys can work on the labs, you guys are coming to lectures, we're doing good. So in this case, this is a chloroethoxy methane. Reason I put it up here is to show you the chlorine isotope pattern that you can see. And again, we're getting to various fragments coming off. You can figure out what fragments are coming off. But in this case, the chlorine is maintained. And again, you'd report this one at what, about 80, 90 something, 92. The second one would be about, 40, 50, let's see, 50, 60, 70, 80. This is about 64. And this is about 121, 122. And again, when you look at the NIST web book, I think it gives you a list of peaks. So you don't quite have to go and do this sort of estimating the way I'm trying to do it here. All right, so let me stop there for a minute. Let me have you gather your thoughts for a few minutes. Take a look at the handout and go through the mass spectra and the chromatogram for the GCMS experiment. Let me think if you have any. Do you have any questions about it right now? Or is everyone good with it? All right, everyone's good with this? All right, Monday it is. Let me finish up those mass spec interpretation problems from Monday. So let me switch gears here and see if I can find that one somewhere on here. Remember, I left you with two of them to do from Monday. Let's finish those two up real quick. All right. Anybody work on this, or do you want a few minutes to think about it? No. You should be able to label each fragment, at least get a good idea what it is. Anybody know what this molecule is? No. isotope pattern doesn't match. If I had two oxygen, if it were peroxide, and I had two oxygens on it, first of all, you couldn't explain the 1.1 because your molecule doesn't have any carbon on it. But the second thing, I'd see something at 36 with about a 0.4 intensity because of two oxygens. So the stable isotopes in their intensity is really critical in trying to interpret this stuff. So let me ask you, let me just go through and ask, how many carbons does this thing have? And this is what you should be asking yourselves when you're doing this. How many carbons does it have? So you look up. So how'd you get two? Why do you think it has two carbons, Nicholas? Yeah, but that's not how we do this. That's not how we do it. You're barking up the wrong tree. Absolutely wrong. How do I determine how many carbons there are? You never do it by dividing. We're using the stable isotopes. So I determine how many carbons by looking at this versus this. If I see 1.1 is my A plus 1 to the 100, do you see the pointer? Yes or no? Nope. Okay, let me do it again. I see it on mine. You guys see the pointer now? Yay! All right. Okay. So what I'm looking at, I'm never going to divide this number by 12 or 19 or 22 or whatever. All right, what I'm going to look at is the ratio, 100 to 1.1. If I see a 1.1 here, what does that tell me about the number of carbons that are in this 34 peak? Exactly, one carbon. I got one carbon. That's it. Now, I don't see any other like 36 peak. Yeah, 1.1% carbon 13. I don't see any other peaks in here that are isotopic. So I'm going to go to my background and I'm going to go, or to my background. My backup plan is, can I figure out how many hydrogens are on this sucker? And I got 1, 2, 3 hydrogens. Could you see these are each losses of 1, 33 to 32. And 34 to 33 loses 1, 33 to 32 loses 1, 32 to 31 loses 1. So I got something that has one carbon. So I got one carbon and 3 hydrogens. That equals 14. Now what do I do? Anybody guess what's left? Oh, that's not right. Somebody needed to fix me. I'm stupid. All right, let's try this again. 1 carbon, 3 hydrogens. That gives me 15. Yep. What is 34 minus 15? Yay, it's fluorine. That's it. Good job. So you got fluoromethane on this one. Do y'all see how we do it? All right, let's do the last one. All right, guys, cognitate on this for a minute or two. Anybody know what molecule this is? So again, you got the 100 peak here. What's disconcerting is the 89 here. So my guess is the 100 is not your molecular ion. the 29 isn't your molecular ion, but your 30 is. If I assume the 30 is a molecular ion, what does the 31 tell me about how many carbons there are? Exactly, I got one carbon. So let me write that down. Because it's around 1.1. Let me go look at here. Because it's around 1.1% of this. I mean, it's really 1.3. But there aren't any isotopes that are going to give you just 1.3. So it has to be a combination of isotopes. So we know we can get about 1 from the carbon being here. And then we got to worry about what this 0.3 or 0.2 is from. So we know we have 1 carbon. 1.1. Hold on. Damn it. It disappeared too fast. Hold on, Daniel. Let me zoom in. Yes. Yes. It's going to be the A plus 1 or the A plus 2. Right. Yes. If there's 2, then it's simply going to be 2.2% instead of 1.1%. Exactly. So I got to figure out, so what isotope has an A plus 2 that might be around 0.3? What atom has a stable isotope that has an A plus 2 with an intensity of about 0.3? All right, let's hit it from another angle. No isotope. Don't give me the whole thing yet. Let me ask you this. How many hydrogens does it have? Because I go from 30 to 29 to 28. That tells me I only have 2 hydrogens. So I can do the same thing I did before. I can go 12, 14. Thank you. It's formaldehyde. So what you have for the 1.3, it's basically a combination of C13 carbon, H2O. This would be about what? About 1.0. And it's carbon 12. And that's close to the 1.3. Do you all see how we get to 1.3 here? For the 31 peak? And the carbon 13 for the 29 peak is just buried under this 89. It's just, you ain't going to see it. All right, so it's formaldehyde. Any questions? Yes, go ahead. You can use your mic. Yeah, generally these differences of 1 mass unit are losses of hydrogens. Exactly. That's okay. So how do you get 10? Because it stops right here. The loss of hydrogen is basically from 30. Let me do this. Oh yeah, you could do. You're probably never going to get to 10, but you're going to do 4, 5, or 6 on some of these molecules. But generally, it's 3 or 4. You know it has hydrogens. And losing different hydrogens from different places is going to give you the same mass loss. All right. Any other questions? All right, guys. Have fun with the lab. And I will see you all on Friday. If you got questions, you can email me. That'll work too. Yeah, we're doing PChem today. I didn't do PChem on Monday because I figured a bunch of you were still trying to finish up on the exam. So that meant you guys weren't going to really pay attention to me at all. We're going to go start under molecular forces today, okay?